Hello everyone, I'm Apostolos Zormpas. I'm a PhD student and I'm working in LMU Munich in the group of Tim Birnstil. And in this talk I will talk about disk population synthesis and a work we are doing in collaboration with Giovanni Rossotti in Leiden. So a couple of years ago there was a sub-arcsecond resolution survey of the dust continuum emission from 50 nearby protoplanetary disks. And the important result of this survey that was published by Tripathi et al. 2017 was that the luminosity of the disk scales with the emitting area, or more specifically, the emitting area is proportional to the square root of the luminosity. We will refer to this relation from now on as the size-luminosity relation. As area here, they define the radius that encloses 68% of the total disk flux, and it's referred as an effective radius. So we had the idea to reproduce these results in a large scale and find out which initial conditions can give us disks that lie on the size-luminosity relation. We did this by performing models of gas and dust evolution using a slightly modified version of the 2-poppy model by Birnstil et al. 2012, and we recreate this relation by using an extended parameter grid while varying the initial values of the turbulence parameter alpha, the disk mass, the stellar mass, the characteristic radius, and the fragmentation velocity. For every parameter, we shuffle between 10 initial values, and by taking all the possible combinations between them leads to a total of 100,000 simulations. The range of the initial conditions was based on recent simulations and observations. Moreover, we also included planets, or to be more specific, we mimicked the effect of the planet in the disk by using the prescription from Kanagawa et al. 2018. We performed simulations with 3 different planet-to-star mass ratios, as we see here, and for reference, 10 to the minus 3, it's a Jupiter mass planet. The next step was to define what is considered the size-luminosity, as to consider it as a simulation that stays on the size-luminosity relation. So we took the plot from Tripathi 2017 and we overplotted the data. Then we took the disks that lie on 1 sigma above and 1 sigma below the size-luminosity relation according to the data from Tripathi. Here we saw what an evolution track is, and it's the path that the simulation follows on the size-luminosity relation in its chosen time span. Our simulations run for 10 million years, but the time span we chose to plot the evolution track is from 300 kilo years to 3 million years. The thought behind this is that at roughly 300 kilo years, so the beginning is somewhere here, our disks reach a quasi-steady state, and at 3 million years, they are at a state that evolves very slowly since there is not much dust left around. From this figure, we also define a simulation as survived or failed. Survived is only if it starts and finishes inside the size-luminosity relation, and in this case, this is only the red one. But now the question is how every parameter of the ones that we alter affects the evolution tracks. In the next slides, I will show you some examples of that. So the first one to explore is the dependence on the planet position. We simulate 4 different cases, one where we have a smooth surface density profile, like in Rossotti et al. 2019, one where we add the Jupiter-like planets at the 2/3 of the RC, one where we move the planet further in at 1/3 of the RC, and one where we have 2 planets in these positions. In this figure, we saw an example of the evolution tracks of a disk with the same initial conditions, varying only the presence and the position of the Jupiter mass planet, as I explained. With the red one, we see the evolution track of a disk with a smooth surface density profile. In a smooth disk, the evolution track will evolve towards smaller radius and smaller luminosity as the dust is lost due to radial drift. When there isn't any planet, there is no bump to halt the dust from drifting, leading to the complete depletion of the disk in the first million years. Now, if a planet is present, the pressure bump that is formed stops the dust from drifting towards the host star, delaying the evolution of the disk on the size-luminosity diagram, thus keeping the tracks on the size-luminosity relation for longer times. With this in mind, we have a shorter evolution track when we include the planet. But when the planet is in the outer radius, the track is indeed much shorter, like the yellow and the green one here. On the other hand, when the planet is in the inner radius, they have a similar track to the one with the smooth case, in this case, the purple one. This leads to the conclusion that the planet close to the star will not affect dramatically its track in the size-luminosity diagram, but the planet in the outer part will do. If we include now 2 planets, one at the outer part and one at the inner part, we observe a similar evolution track to the case where we only have 1 planet close to the outer radius, with the disk being slightly more luminous, in this case the yellow one. This is also explained by the fact that the dust from the outer disk stops at the outer pressure bump. while the dust that exists inside the outer planet stops at the pressure bump of the inside planet. Since most of the disk mass is in the outer part, the dust that is trapped between the two planets contributes only partially to the total luminosity. So the important conclusion from this is that when two or more planets are present, the outer one is the most dominant in the evolution track. Furthermore, this might suggest that when two planets are formed in a planetary system, the inside planet should be formed first. Otherwise, the mass reservoir will be limited by the outer planet. Next, we show how the alpha parameter affects the evolution tracks. The effect of it is not very straightforward. In this figure, we show the evolution tracks of a disk with the same initial conditions, varying only the alpha parameter, as I said. So we choose a disk where we also have inserted a Jupiter mass planet, since the effect here is a bit more prominent on these disks. So we have alpha values ranging from 10 to the minus 4 to 10 to the minus 2, and we see the trend here. Disk with low to medium alpha has smaller luminosity than disks with higher alpha values. So red, blue, and green line. This is because the ring that is formed due to the planet is becoming too narrow and optically thick. This is easily explained since the total flux emitted by an optically thick ring of a given temperature is just a function of the emitting area. So lower alpha will just lead to a narrower ring, so less emitting area, independently of the amount of mass in the ring. Therefore, we always have smaller luminosity. On the other hand, various processes work against trapping when we have high alpha values, and consequently leading to more luminous disks. When we are in the fragmentation limit, for example, the particle size decreases and produces grains that are less efficiently trapped. The diffusivity also increases, so allows more grains to escape the bump. The viscosity increases, so more dust sizes are traveling with the accreting gas. The pressure peak also smears out, causing less efficient trapping by radial drift. If we consider the two cases where the alpha value is too high, we observe less and less trapping, and the evolution track is getting longer because the planet cannot efficiently trap, and the disk evolves further along the size-luminosity relation to smaller luminosities. One of the biggest problems in our models is to find out which feature has the biggest impact on the final outcome. So in order to solve this, we set up a neural network and we use a method called permutation important. The question that this method answers is the following. If we randomly shuffle a single column of the validation data, leaving the target and all the other columns in place, so the target in our case is to stay on the size-luminosity relation, how would that affect the accuracy of the predictions in the now shuffled data? So the accuracy especially suffers if we shuffle a column that the neural network relied on heavily for predictions. So in this case, shuffling disk mass, characteristic radius, and alpha causes bad predictions. So the higher the percentage you see here, the more important every parameter is. If we shuffle the stellar mass instead, the resulting predictions do not suffer nearly as much. So we conclude that the most important parameters are the first three ones. So then we had to do some statistics, and in order to identify trends between the initial conditions and the survival frequency of every disk, we construct these histograms where on the y-axis we have the survival frequency, so meaning the percentage of simulations that survive the size-luminosity relation, and on the x-axis we have the value of each parameter in our grid model. The bars are some representative cases that we tested with or without planets. With black color, we saw the simulations that we used a smooth surface density profile, as in Rossotti et al. 2019. In the first figure for the alpha, we see that regardless the case, our simulations tend to favor low values of the turbulence parameter. These results have already been explained from the evolution tracks before. Low alpha values lead to efficient dust trapping and allow the disk to retain its mass. On the other hand, as we move to higher alpha values, the trapping stops being efficient anymore, leading to higher chances that the evolution track will leave the size-luminosity relation in the selected time span. In the next figure, we plot the survival frequency of the disk mass values that were used in our models. The tendency here is that higher disk masses leads to more simulation inside the size-luminosity relation. And the reason to this is that high initial disk mass places the disk initially above the size-luminosity relation until they reach a stable state. While the dust is drifting inside, the luminosity decreases, allowing them by our chosen time span to reach the size-luminosity relation and stay there for the remaining time. The difference becomes striking between the smooth and the planet case, so the black and the other colors. If we don't have any planets, the disk mass is not a major factor in the evolution of the disk, since all the values have roughly the same survival frequency. So to summarize, Substructures need to form in the first million year, otherwise there will be nothing to stop the dust from drifting towards the star, leading the tracks outside of the size-luminosity relation. The introduction of planets widens a lot the parameter space that follows the size-luminosity relation. So we need to have substructures or planets. When two or more planets are present, the outer one is the most dominant one for the evolution tracks, and the inside planet might have to form first, otherwise there will be a limited mass reservoir. And in the end, we observe a trend towards low to medium alpha values and high disk masses. Of course, there are many more conclusions that will be presented on the paper, and if you have any questions, feel free to ask me via email or Slack. Thank you for your attention.